So now that we've talked a little bit about Java 8 streams, I'm going to continue on. Now, if you recall last time, I just gave you sort of the bare bones discussion about what streams were, and we talked about how they had multiple parts. You have to get a source of data from somewhere. You have to be able to run that data through what are called intermediate operations that can filter or transform the data in some way or another. And then we talked briefly about this concept of terminal operations, which are operations that finish the stream and maybe return a result or maybe have some side effect or whatever. And so now we're going to talk about some of the common stream aggregate operations. And this will, of course, fit nicely in with your next assignment where you have to implement some of these things. The operations we're going to talk about apply both to sequential streams and to parallel streams. Now, again, your assignment 2 is going to be all about sequential streams. And then the good news is once you master the sequential stream, going to the parallel stream in assignment 3 will be really, really, really simple if you get the sequential stream working properly. And as a rule of thumb, being a good streams programmer, a good sequential streams programmer, is almost guaranteed to make you a better parallel streams programmer, and maybe even vice versa. So once you know about parallel streams, you can write your sequential streams better because you can find the lurking bugs in your sequential streams that didn't show up because you never ran them in parallel. And we'll talk a bit more about that. We'll use a simple example throughout the slides to demonstrate and reify, fancy word, reify the discussions, the concepts. I always like to try to have, as much as possible, every abstract concept anchored with an example. And you'll see that the examples will be both code and also visual. So you can kind of get a left brain and a right brain view of this stuff. And you can grab the example from my website. All right, so what's this example? This example simply uses a stream to find words in an input string. So we're going to search for real simple things. We're going to search for the names of musical notes. And the input string we're going to search is something that has the names of musical notes, which is the Do Re Mi song from The Sound of Music. So you can look at that if you're curious. So this will illustrate some of the aggregate operations, and we'll use these throughout other parts of the lessons and other parts of the assignments. So map, filter, and collect are the things we're going to talk about. Now, the way this is going to work is you're going to basically run this program, and it'll go through the song lyrics, and it'll search for the words, and then it'll print a result at the end that says, word re matched at all these indices in the input string, in the text, or word t matched at these indices, right? So it's basically giving you a mapping of what word appeared where in the input string. So that's just what the output looks like. Okay, so let's first talk about how this stream is going to work. It's really pretty cool, and I'll try to visualize it first. Now, the key thing to remember as we go through this discussion is the visualizations are here purely to help you think more clearly about what is logically going on under the hood with streams, which can otherwise be somewhat abstract and daunting. But the way it physically works is not exactly the way it works logically. However, it doesn't matter. You should think about it sort of in a logical sense, and then the implementation will be super duper optimized to make it work really fast. And so don't get confused with the pictures and the reality, but the pictures that help you think conceptually about what's going on. So what happens here is we're going to give a set of words, which is going to be a list of words, actually, and we're going to say to that list of words, list.stream. And stream is what's called a factory method. And what the factory method is going to do is it's going to convert the list collection into a sequential stream. Remember, a stream is just a flow of data elements that are going to be able to be transformed in one way or another. Okay, so this is the conceptual view of the list of strings. Imagine that the greenish thing is like a list collection, and the little square, the gray squares, are strings. So this will then create a stream of strings, right? So list of strings goes to stream of strings, and that's the consequence of calling the stream method on the collection. Now, again, logically speaking, all these things get transformed and so on, and we take a collection and we output a stream. This stream is then logically given as input into the next operation, which happens to be an aggregate operation, or more precisely an intermediate operation, right, because it appears between the source of input and the terminal operation that's coming. And what this will do is this is going to go ahead and map each element in this stream through the search for word behavior. So this right here is what's called a method reference. Remember method references? We talked about those. It's a form of lambda. It's a sort of a shorthand for a lambda. So what this is saying is for each of these words here, which are each one of those a string, like do, re, mi, etc., go ahead and look in the input to try to find where that word appears. And that's what map is doing. So it's saying for each of the elements in the stream, call the search for word method on that particular element. So search for that in the string. And what that yields is an output stream. So we take in an input stream of strings, and we return an output stream of so-called search results. And you can tell visually that I changed from having these gray squares to these orange or gold circles. Right? So all that's doing is showing the type changed. So that's one thing that map can do. One thing that map can do is it can change from one type to another because of the function that's applied. Yes, Matt?
If we were to have our own collection, would we have to implement a two-stream method in order to get this to work?
Great question. So if you have your own collection, and in fact, you do have your own collection. It's called array. And if you look at array, you'll see that it has a stream method on it, which I give you, and the implementation of stream says return stream support dot stream open paren splitterator and then false for the stream. So that's already provided. So yes, that's if there's a collection that you implement, you have to implement stream if you want it to work with streams. And of course, all the ones that come pre-built into the Java class library already have high quality stream implementations, stream factory methods defined on them. Good question. OK, so notice again what's happening here. We're transforming one type to another. That's one thing that map is doing. And we're also doing something, right? We're searching for something. And there's a lot more profound things we'll talk about shortly, but that's the quick synopsis of what this thing is doing. Now again, keep in mind that the way that this looks here, it's almost as if we're taking one stream and then applying the operation on every element, and we produce a brand new stream. That's actually not what's happening under the hood, but logically that's what's happening. So don't freak out and think, oh my God, there's so much overhead, there's new streams being created galore. No, it's actually cleverly optimized to be really efficient, but logically speaking, that's what's going on. All right, now what we're going to do is, if you look up some of these words, it might turn out that they don't appear anywhere in the input. Now, if you're going to look up the do, re, mi words in the do, re, mi song, you'll probably find all the words in there. But more generally, if you were searching, the do, re, mi words in the works of Shakespeare, there might be some that don't even appear at all. In fact, probably a lot of them don't appear because Shakespeare wasn't writing songs, right, for the most part. So one of the things we're going to do here is we're going to apply a filter operation. And what filter is going to do is it's going to remove the empty search results from the stream. So the way you read filter is, if anything is not empty, then let it go through, right? So what that's saying is filter out stuff that's empty and filter in stuff that's not empty. Okay, so we're saying just let the stuff that actually had results go through. That's what filter's doing. And so what that can do is that can return a subset. It'll return a new stream that only has some of the elements that were in the input stream, right? So input stream was all the elements. The output is the ones that match. Now, unlike map, where map can change types but must return the same number of elements, filter cannot change the type but might return less than the number of elements. It could also return equal, of course, if everything matches. In this case, it probably will. But in general, it could return a subset. So that's one way to think about the difference between map and filter. Filter is going to get rid of some stuff, maybe. So you might get less than or equal to the amount that came in, but it'll be the same type, hence the colors are the same. map must return the same number of elements, but they could be transformed to a different type or a different value. Yeah?
What exactly does the map method?
Yeah, all the map method does logically is for every element in the input, it calls this lambda expression or this behavior. So, what this is going to do, we'll look at search for word in just a second. Search for word takes in some values, some parameters, and it returns you a result, which is so it takes a string in, which is the word to search for, and it gives back the search results. So now that we've done all this stuff, we now want to turn this back into something we can actually manipulate in a classic Java way. So we have collect, and collect is going to take in the non-empty search results. It's going to trigger all the operation processing. So remember, none of this took place until collect is called, which is a little weird. That's why we call collect, that's why we call streams a lazy operation. So all the intermediate operations are lazy. They don't actually get run until collect is called. And I'll talk later when we talk about how this works under the hood. I'll explain why it does that, why that is the case. And as a result of triggering all these things, we end up with a list of search results. So we took a list of strings, we ran it through these processing stages, and we have a list of search results as the output. Any questions about that? Of course, we'll come back and talk more about that. So toList, you'll actually have to implement something like toList called toArray, which we'll discuss later. It's called a collector. Anybody here know, has anybody here following the Marvel movies with the collector? Does anybody know what's the collector? He's that weird guy who's probably got an infinity stone, right? So actually, if you're a Marvel fan, I had the most exciting experience a Marvel fan could ever possibly have yesterday. I got to see Stan Lee at the World Comic Con down in Nashville. And it was amazing. The guy's, first of all, he's really, really old. He's almost 95 years old. But totally lucid. He did about an hour Q&A at the panel down there. And really great. He was telling us what his favorite characters were and his favorite movie scenes. And it was just amazing. So not every day you get to see a living legend. And he's certainly a living legend. It was great. OK, so let's talk about these things in more detail now that I've given you kind of an overview. So what is an aggregate operation? So the fancy way to describe an aggregate operation is to call it a higher order function. Does anybody know what a higher order function is? So it's one of those fancy terms that functional programming people like to throw around and makes them feel intellectually superior. It just means a function that can return a function or take a function as an argument. So it's a higher order function. It's a function that can work on functions and return functions. And that's what it does. So basically, an aggregate operation is past a function or behavior more specifically, and it'll apply those things to the data going past. Why is this useful, you ask? Well, I'm glad you asked. The reason it's useful is because it helps us to focus on what we want to do, not how we're going to do it, right? So as a general rule of thumb, the more you can make your programs, especially at the higher levels, be close to the design spec, the easier it is to understand. Once you've figured out how to read the stream syntax, at first it could be a little daunting, but the what is more important than the how from an understanding point of view. Obviously, the how is important too, right? We're not ignoring how, but what is really the key thing. So what you can see here is it's going to process every element in a stream through a processing phase. Again, don't get too caught up in the phases. The actual way that they work is slightly different, but the logical behavior is as though there's a phase or a stage where things get processed. And here are some of the operations: map, filter, and collect. Those are ones we'll work with, along with flat map. So what does map do? Map basically takes in a function, and it applies it to each element in the stream, and it will then return an output stream that consists of the results of that function. It has to apply, it'll have to return the same number of elements as it got as input. So it's just calling that function, that mapper, on every element. Here's kind of how this gets used in the example we were looking at. So you notice how map is going to be used to transform these strings to search results. And there's the same number that came in that come out. And as you can also see here, it can change the types. And that's just because that's the way the function works, right? Function takes an input parameter, and it returns an output parameter, and the input parameter and the output parameter can be different. And you can control that. So in this particular case, it does convert from string to search result, but that just is because of the way the program works. It doesn't have to do that. You can control how that works. Here's the actual code in the stream for doing this. We'll later look at search for word a little bit farther down the road, but that basically is where the code goes. So, again, the way to read this is words to find is a collection. It's a list. Convert that list to a stream. Run every element through map, looking for the word that we're searching for one at a time, because it's sequential, and then pass it on to the next phase. OK, so far so good. Yeah?
Does map have to change the type?
No, it does not have to change that. It's purely a function, pun intended, of whatever the parameters are for this function. So if it goes from t to t, the type change stays the same. If it goes from t to u, where t is the input type, u or r is the return type, then it will change it. OK, so the next thing in the line is filter. As we said before, it basically takes a predicate. And as you may recall, predicate's a functional interface that has a test method that takes a parameter and returns true or false. And of course, the way it's going to work is only if the predicate returns true does the element continue on to the next stage in the string. As you might imagine, then it can return less than or equal to, not just equal. And here's where we use it, right there. And as you can see, in this particular case, as is always the case with filter, you can't change the type of the elements. You can reduce the elements, but you can't change their type. It's just returning true or false. And so it'll either go through or it won't. OK. Here then is the code. You can see that we're going to filter. We're going to filter through. Filter is a kind of a funny word, because filter might sound like a coffee filter, right? What does a coffee filter do? It doesn't let the coffee beans go through, but it lets the water flow through with coffee in them, right? So we're filtering stuff. So this is going to say, get rid of everything that's empty. So let through what's not empty. Yeah, Arturo.
So on that last thing, what do you mean exactly by changing type?
Yeah, good question. So if you take a look at the visualization here, we started out with a list of strings. So string was the type. Then we have a stream of strings. So you can see I kept the icons are the same shape and the same color. But then when we did map, we went from a stream of strings to a stream of search results, because that just tells you what matched. So all of a sudden, it was a string to search result transformation. So we changed the type. The type was no longer string. Now we have a stream of search results.
So map did that?
Map can do that. Map did that, yes. It doesn't have to. If I didn't program it that way, it wouldn't do that. But map is capable of changing the type. And that's because map takes a function. And if you were to look at the function's functional interface, it takes t and r, where t is the type that's the parameter to the mapper function, and r is the return value. So if t and r are the same, no change. If t and r are different, as they are here, string and search result, then it can change it. Yes?
So the not symbol wouldn't work in the filter method, like the exclamation point symbol?
Oh, great question. Really good question. So you'll notice that I used a little not operation, which I had to write because for some strange reason Java 8 doesn't provide one. Maybe they'll fix that in Java 9. I don't know. It's out in a couple weeks. We'll find out. So if I did this because I wanted to use a method reference. So I said not search results : is empty. If I didn't use the not predicate operation, I could have written this to say filter result arrow not result dot size equal 0 or not result size. I could have used the not operation, or I could have used the equal or not equal operator, but I would have had to have used a lambda expression, not a method reference. So I could have done that, and I think I'll show you an example of that a little bit later. Yeah.
So we can think of filters kind of like more of like an allow or permit.
Yes, that's a very good way to put it. It's really more like permit or allow. Yes, that's a good way to put it. Filter is a funny way of saying it. Map and filter are these intermediate operations that process the elements in their input stream and yield an output stream. Again, that's logically speaking. The way things actually work under the hood isn't quite that way. I'll show you that later. So the way to think about intermediate operations is they're lazy. They like don't do anything until they're actually forced to. And they're forced to when a terminal operation is hit. So when we hit a terminal operation, that's when the work actually gets done. And I'll talk more about that in a second. This particular terminal operation, collect, is used to perform a reduction. There's a couple of other methods that do reductions as well, but we're using collect here for good reasons. So what a reduction is it takes a bunch of values and it puts them into a single result. So it's kind of like, you know, merging lanes on the highway kind of thing. In particular, what we're going to do here is we're going to trigger all the processing. First of all, we're going to trigger all the processing, and then we're going to end up collecting the results and returning a list of search results. Now, this picture also gives you a better idea of what's really going on under the hood. So I'll explain it briefly here, and we may come back to it later. So the way that streams actually works, it doesn't actually process every element, you know, in one stream, then create a new stream, process every element. It actually pulls the items down, sort of, at least in a sequential stream, sort of one at a time from the input source, and it runs each element through all the various filters, intermediate operations. And what happens when the code runs and it sees, you know, stream, map, filter, collect, when that code actually executes at runtime, what it does under the hood is it creates an internal linked list of lambda expressions. So every time, you know, as it's running, it'll see .stream, and that'll be a call into a runtime library method. It sees .map, that'll be a call into a runtime library method with this lambda expression passed in. And so it basically builds a linked list of these intermediate operations. And then when it hits the terminal operation, which is the final one, at that point, it triggers everything to start running. And what it'll do, it'll then go and it'll pull the elements from the source through the linked list of processing operations and apply them and get a result. And then it'll take the next item and it'll pull that through the stream, get a result, and so on and so forth. And the reason it does this, there's several reasons it does this. One of the things you have with streams is this thing that's called short circuit operations. So we don't show that here, but one thing you could say is you could say, you know, stream, map, filter, limit, collect, where limit might say, only take the first, you know, 5 elements out of this 3,000 element list. So what happens there is once you hit the limit, the processing stops. It's called short circuiting. And so by doing things in this sort of top to bottom order, the second it reaches the limit, it can bail out. And so even though it looks kind of like every element's done row by row, it's actually logically or physically done by pulling the elements through each of the linked lists of processing phases. So that'll become more clear and more important when we talk about parallel streams. What parallel streams does, again, very quickly, is it will take your input source and it'll break it up into chunks using a splitterator, and then each thread will work on a chunk of the data.
If you wanted to filter on using multiple functions, would you have to call filter multiple times, or could you do it all in one?
Oh, great question. So the question is, if you want to filter on more than just the search results being empty or not, could you make one expression that was multi-part, or do you have to call filter multiple times? It kind of depends on what you're doing. If you can do all your filtering in one phase without having to transform it again, then you would probably pack them into one complex expression. But you might have to filter things in different stages after they're transformed by map operations. So if that was the case, then you'd have to kind of layer them, you know, later in the pipeline. But I think the real question that you're probably asking is, can you call filter multiple times? And the answer is yes. As a general rule of thumb, if you have a really complicated stream pipeline, you might want to break it up into pieces because it gets sort of hard to understand. But certainly, logically speaking, you could do multiple filter operations per pipeline. So here's what the code looks like: collect to list, and to list is what's called a collector. And what this will do, and you guys will get some experience with this in the next programming assignment, is it takes the stream of elements and it goes ahead and it accumulates them into a data structure, which in this case is a list. And then when it's all finished, it'll return that data structure as the result of the collector collect operation. So the collect will give you back a single thing, which, as you can see here, we store in a list of search results. OK, so that's the end of this overview.